All right, welcome back. We're going to be talking about wave-particle duality, which you did some reading on just now. The big idea with wave-particle duality is that all matter can behave like waves or particles. It's just that the more massive the thing is, the more it behaves like a particle. If you're thinking of something behaving like a wave, you want to think of a sound that can exist in more than one sound can exist in the same place. And the fancy physics word for that is interference. The other thing when you think about waves is that you don't have to see somebody to hear them. So that means that waves can go around barriers. And the fancy physics word for that is diffraction. Now, when you're thinking about particle behavior, particles bounce off of each other. And the fancy physics reason for this is because the particles have momentum. So to take this idea of the more massive the particle is, or the more massive the thing is, the more it behaves like a particle. Electrons are pretty much the smallest thing that have mass, but that don't have a lot of it that we'll consider. So they will interfere the most of anything that has mass. They'll diffract the most of anything that has mass, but they'll have the least momentum. So they'll bounce off of each other the least. So electrons are going to be in more places than at once. That's why we have that cloud model from chemistry. If you talked about that, they're going to go around barriers in weird ways more than other things, but they're not going to bounce off of each other as much. Protons and neutrons, on the other hand, have much more mass, so they're going to have little interference and little diffraction, but more momentum. So they're not really going to interfere with each other much. They're not going to diffract around barriers as much, but they are going to bounce off of each other a lot more. Anything else is pretty much only going to bounce off of. So if we think of electrons on this side, right, and light or electromagnetic radiation on this side, we can think of electrons acting like waves when they diffract. And light or electromagnetic radiation, even though it has no mass, right, that's going to mean it's the less mass, the more it behaves like a wave. So it's going to behave mostly like a wave, but sometimes light or electromagnetic radiation is going to act like a particle. And that's going to happen when it has momentum and bounces off of things. Then we can go through this example problem. Electron momentum doesn't support the theory that matter has wave nature, because momentum, that's a particle behavior. So we can cross off both of the ones with momentum. And then photon diffraction, well, that's not really matter, because photons are, we'll talk about them later on, but they don't have mass. This is light. So that's not the best answer. The best answer is going to be that electrons diffract, right? We shouldn't expect that to happen, because we should expect them to behave just like particles and for them to just bounce off of things. But instead, sometimes they're going to diffract around barriers. Okay, so what is a photon? A photon is a packet of electromagnetic energy. Equation that describes how much energy that is going to be exactly related to the frequency. So that's energy equals H, which is Planck's constant times F. So that's H is 6.63 times 10 to the minus 34 joules seconds. And then because we can rewrite the frequency of an electromagnetic wave in terms of its wavelength, we can say that this is also hc divided by lambda, where c is the speed of light. H is Planck's constant. That's just a guy who figured out what a photon was. And E photon is just the energy of a photon. Now, joules is a pretty big unit of energy, so sometimes we'll describe the energy of a photon in a different unit called an electron volt. But 1 electron volt is just equal to 1.6 times 10 to the minus 19 joules. I know it's a weird number, but it's just a conversion factor. So we can do an example. Like, let's say we had 5 times 10 to the 8th joules, and we wanted to convert that into electron volts. So I can start off by writing out that energy in joules, 5.0 times 10 to the minus 8 joules, and then I want to multiply it by my conversion factor. So I want joules down here so that that cancels out, and electron volts up here. Well, I know 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So I can just punch that into my calculator. I don't need to cross multiply because that's just a multiplication there. It's just 5.0 times 10 to the minus 8 times 1, then divided by 1.6 times 10 to the minus 19. And when I punch that in, I get 3 times 10 to the 13 electron volts. And I can also just calculate energy using that equation, right? So let's say I'm given a frequency. So my frequency is 5.0 times 10 to the 14 hertz, and I want to know the energy. So I want to know the energy of that photon. Well, I can just use the equation E photon equals h times f, and then I can plug in numbers. Well, I didn't write h yet, but I know that h is Planck's constant. It's on the front of my reference tables. If you forget it, it's right here. Put those numbers into my equation, and I got 3.3 times 10 to the minus 19 joules. So in this last example, I'm given the energy electron volts. That's 2.11 times 10 to the 11 electron volts. And the first thing I want to do is find that energy in joules. So I'll multiply by the conversion factor, where I have electron volts down here and joules down there. Well, that means that that's 1.6 times 10 to the minus 19 joules, and that's 1 electron volt. So my electron volts cancel out, and I get in joules, that is 3.38 times 10 to the minus 19 joules. Now I want to find the frequency, so I'm actually going to want to come back to that equation where I have E equals h times f, and I'm going to want to make that a triangle equation. So if I cover up E, I have h and f next to each other. So that means I put h there and f there, and I put E up top, which tells me that frequency is energy divided by h, and then I can plug in numbers into that equation. And because that's in joules, I'm going to want to use the energy in joules from over here. I punch that into my calculator, I get a frequency of 5.09 times 10 to the 14 hertz. And then I want to determine the color of light, so I want to go back to my reference tables and find 5.09 times 10 to the 14 hertz. And 5.09 is going to be somewhere between 5.03 and 5.20, which means I'm in the yellow range. So thank you for tuning in again. I hope you're enjoying your time learning modern physics.